Let's learn about the transpose of a matrix. Let's begin with an example. Given a 2x4 matrix A, so a matrix A that has 2 rows and 4 columns, the transpose of A, which is often denoted with an A with a T next to it, is a 4x2 matrix. So 2x4 becomes 4x2, whose columns are given by the rows of A. So here's the first row of A. That becomes the first column of A transpose. 1, 4, negative 2, 7. 1, 4, negative 2, 7. And the second row becomes the second column of A transpose. More generally, if A is an M by N matrix, so a matrix with M rows and N columns, then A transpose is an N by M matrix. So the number of rows becomes the number of columns, and the number of columns of A becomes the number of rows of A transpose. And the matrix A transpose is obtained by making the rows of A into columns of A transpose. How does this transpose operation interact with the other matrix operations we've seen? Let's find out. Given two matrices A and B, both of these are 2x4 matrices. They have 2 rows and 4 columns. We know how to add these. We add these 2 matrices by adding corresponding entries. So, for example, this 1 and this 2 add up to make up this 3 right here in the sum of A plus B. Then we can find the transpose of A plus B, namely A plus B transpose, by taking the first row of A plus B and making it into the first column of A plus B transpose, and taking the second row of A plus B and making it into the second column of A plus B transpose. Alternatively, we could take the first row of A, that becomes the first column of A transpose. Similarly, the first row of B becomes the first column of B transpose, and the second row of A becomes the second column of A transpose. The second row of B is the second column of B transpose, and we can then add these 2 transpose matrices to each other and end up with A transpose plus B transpose by simply adding corresponding entries. For example, this 1 and this 2 add up together to form this entry of the matrix A transpose plus B transpose. Now we notice that the matrix we obtained earlier by taking A plus B first and then taking the transpose is actually the same as the matrix we just found by first finding A transpose and B transpose and then adding the results to each other. We can collect this result in a little fact. If A and B are matrices of the same size, then A plus B transpose, which means finding the sum first and taking the transpose of the sum, is the same as finding the 2 transposes individually and adding them up. In other words, the transpose operation commutes with the addition of matrices. Let's find out how the transpose interacts with scalar multiplication. Let's again look at an example. A is a 2x4 matrix, 2 rows, 4 columns. And we know how to find 3 times A. We simply multiply each element of A by 3 to obtain the elements of 3 times A. So the transpose of 3 times A is then found by taking the first row of 3A, making it into the first column of 3A transpose, and similarly taking the second row of 3A and making it into the second column of 3A transpose. Alternatively, we could have also found the transpose of A first and multiplied that by 3. Would that have yielded the same result? Let's find out. Here's A transpose. We take the first row of A, it becomes the first column of A transpose. We take the second row of A, it becomes the second column of A transpose. And then we multiply that result by 3. So for example, this 1 here is multiplied by 3 to give rise to this 3 right there. And again, we notice the results of 3 times A transpose, or taking 3A first and then transposing the result, those 2 matrices are the same. We record this in a fact again. If A is a matrix and lambda is scalar, then we can either multiply A by the scalar lambda first and then find the transpose, or we can find the transpose first and multiply the result by the scalar lambda. The result is the same. How does this transpose interact with matrix multiplication? Let's start with some observations. Recall that in general for 2 matrices A and B, matrix multiplication is not commutative. So you cannot take AB or BA and expect the results to be the same. In fact, it may even be the case that AB is defined but BA is not. Here's an example of such a situation. Suppose A is a 3 by 2 matrix, so it has 3 rows and 2 columns, and B is a 2 by 4 matrix. Then A times B can be found, and this is so because the inside dimensions agree. And the resulting matrix is going to be a 3 by 4 matrix. So AB is a 3 by 4 matrix. But you cannot find B times A because B is a 2 by 4 matrix and A is a 3 by 2 matrix. So now if I wanted to multiply B times A, my inside dimensions don't agree with each other. And so I cannot multiply B times A with each other. Can I multiply A transpose by B transpose? A transpose is then a 2 by 3 matrix and B transpose is a 4 by 2 matrix. So it does not make sense to multiply A transpose times B transpose because the inside dimensions don't agree with each other. However, if I look at B transpose times A transpose, then the inside dimensions actually do agree with each other, and the result is going to be a 4 by 3 matrix. In fact, it is true in general that if A and B are matrices such that their product A times B is defined, then the transpose of A times B can be found by taking the transpose of B and multiplying it with the transpose of A. So notice that it's B transpose times A transpose, not A transpose times B transpose. So you have to flip the order here in order for the dimensions to make sense. Finally, what happens when you take the transpose of a matrix? Let's look at an example. Here's my matrix A, which is a 2 by 4 matrix. Then A transpose is found by taking the first row of A, making it in the first column of A transpose, taking the second row of A, and making it into the second column of A transpose. Now if I wanted to find another transpose of A transpose, I would have to start with the first row of A transpose, making it into the first column of the transpose of the transpose. The second row of A transpose becomes the second column of the transpose of the transpose. The third row of A transpose becomes the third column of the transpose of the transpose. And finally, the last row of A transpose becomes the last column of the transpose of the transpose. If I take a good look, I notice that the matrix A agrees with the transpose of A. That's not really all that surprising, right? We flipped rows and columns twice, and so we ended up where we started. But we can still collect this in effect. For any matrix A, we have that the transpose of A goes back to the matrix A itself.